The buoyant force and Archimedes Principle are going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now we've all had the experience of going into the water and feeling a little bit lighter, or lifting something underwater and having it feel a whole lot lighter. And the truth is, its weight has not changed, but now there's an upward force on that object we call the buoyant force, and that's going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So we'll start with talking about the nature of this buoyant force. And we're going to take a look at a sphere here of some unknown substance. I'll tell you what the substance is in a little bit. But that's completely submerged underwater. So we learned that when something is submerged beneath a fluid, there is a pressure exerted on it. It's exerted on all sides. So there's a force from that pressure applied to every area of that surface. And so in all directions here, there's a force being applied due to the pressure on it. Now the horizontal components will be exactly equal in magnitude, but opposite direction will cancel, but that's not going to be true of the vertical components. We learned in the last lesson that as you go deeper and deeper and deeper into a fluid, that the pressure goes up. And as a result, the pressure that's exerting a force on the bottom half of this structure is actually greater than the pressure that's exerting downward on the top half of the structure. And so overall, we end up with a net force in the upward direction. That is the buoyant force. And it's just due to this difference in pressure and the resulting force that's being applied to the bottom side versus the top side of an object. All right, so now let's take a look at this substance here. I'm going to tell you that the substance that is this sphere is actually water itself. So, and it's this kind of like imaginary, we're just going to envision this sphere of water that's in the middle of a bunch of other water. So it's not in a container or anything like that. We're just kind of isolating in our minds this sphere of water. So, and we're going to draw a free body diagram for it. So, well, this sphere of water is going to have its own weight, mg. So, but now we just learned that it's also going to have this buoyant force in the upward direction, net. And in this case, it's water, surrounded by a bunch of other water. And so this water surrounded by water has no propensity to rise or fall. It has no net acceleration and no net force in that vertical direction. And that's how we know that the buoyant force must equal the weight, because some of the forces in the y direction are adding up to zero. It's in equilibrium, if you will, in that vertical direction. Horizontal as well, it turns out, but in that vertical direction. So now we've got a way of calculating the buoyant force for this imaginary sphere of water. Now, what if it wasn't water? What if we replaced this sphere of water with, say, a sphere of iron or any other substance? It wouldn't matter. Well, it turns out then the weight would definitely change, but the buoyant force would not. Because that buoyant force, again, the nature of it was just the difference in pressure on the top side and the bottom side of a sphere, which was just due to its size and shape, its volume. And that's all that matters. And so it turns out that the buoyant force, therefore, is just equal to the weight of the fluid that's being displaced. And that's where this comes from. The buoyant force equals the weight of displaced fluid. So if we take a look at that, then we can write this another step down the road. We can say it's equal to the mass, and we'll write the mass of displaced fluid times gravity. And keep in mind that density was equal to mass over volume, and so density times volume equals mass. And so we can substitute in for mass in this expression, density times volume. And that's ultimately where we're headed here. So we're going to have density of the fluid. And in this case, it's not the entire volume of the object that's submerged. In this case, in all cases anyways, because it's not always completely submerged. Now, if it is completely submerged, then this would just be the volume of the object. Because the volume of the object, all of it would be displacing fluid, so the volume of the object would be the volume of displaced fluid. But what if this object was only partially submerged? Well, then it's only the part that's beneath the surface that we'd actually have to account for, because that's the only part that's actually displacing fluid. And so that's why we're going to, in this case, say that's the volume that is submerged below the surface, and then again times gravity. So, and that's going to be our lovely expression for the buoyant force. And we're going to transfer that down below here. All right, so there's our buoyant force. We're going to do some calculations with this. It was Archimedes that discovered this. So, and this is ultimately the end result of Archimedes' principle, coming up with an expression for this buoyant force. So once again, we're going to envision having a sphere of some substance completely submerged in water in this case, and draw the free body diagram here. We're going to have its own weight below and the buoyant force above. But now we want to factor in what these are equal to. And so again, the buoyant force is equal to the density of the fluid. And in this case, I'm actually going to write the volume of the object because it is completely submerged. The volume that is submerged is the entire volume of the object. So in this example, because it's completely submerged, we can use that. And then times gravity. And then down here below, mass times gravity. And again, keep in mind that mass is equal to density times volume. And so in this case, it's going to be the density of the object. So we're talking about the object's weight, not the weight of the displaced fluid now. So times the volume of the object and times gravity once again. And we'll see the only difference here then between the upward force and the downward force, it's not gravity, it's not the volume of the object, it's the density of the fluid versus the density of the object. And this ultimately is why if you have a substance that's more dense than water, it will sink. Because if the density of the object is bigger than the density of the fluid, then the object's weight is going to be larger than the buoyant force, and the overall downward force is going to win, and it's going to sink and accelerate to the bottom. Now, on the other hand, if the object is less dense than water, so if this density here for the object is lower than the density of the fluid, then all of a sudden now the upward force, the buoyant force, would be greater than the object's weight. And if you release it underwater, it would float towards the surface. And so now we have like a mathematical reason why objects that are more dense than water sink in water and objects that are less dense than water float to the surface. It's just what's bigger, the weight of the object or the buoyant force acting on the object? Okay, the second situation we want to envision is one in which an object is actually floating in the fluid, in this example, floating in water. And so we realize that for an object to be floating in a fluid, it must be less dense than the fluid based on the line of reasoning we just had in the last example. So in this case, we've got an object that is less dense than water, and we're going to verify that here in a little bit. And we want to draw a free body diagram for this again. And once again, we have the object's weight down below, mg. And then we have the upward buoyant force, which I'm going to write in a different color here, FB. Now for the object's weight here, I want to rewrite this again just like we did in the last example. Mass is equal to density times volume. And then we'll have the times gravity as well. And again, this is the density of the object here for the weight of the object and the volume of the object. Now it's going to be a little bit different for the buoyant force, but notice again, buoyant force is equal to density times volume times gravity as well. But the key difference is that's the density of the fluid, because it's equal to the weight of displaced fluid. So times the volume, and in this case, again, it's not the entire volume of the object necessarily. That's only true if it's submerged, but it's only the fraction of the volume that is actually submerged. So the volume submerged, and then again, times gravity. All right, so if we take a look at the free body diagram now, again, this thing's in equilibrium. There's no net force and no net acceleration in the vertical dimension. And so that means that our buoyant force must be equal to the weight of the object. So the density of the fluid times the volume submerged times gravity must be equal to the density of the object times the volume of the object times gravity. So in this case, we're going to ignore the contribution of gravity for a second because it's the same in either case. But we want to look at the difference between the volume submerged versus the volume of the object and the density of the fluid versus the density of the object. Now, once again, we already said that we knew that the volume of the object was lower than the volume of the fluid. That's why it's floating. So we also now can see visually that the volume of the object is larger than just the volume that is submerged. And this is important here. We're going to come up with a mathematical relationship. So it turns out in this example, for an object that's floating, we can actually say that the density and the volume are going to be inversely proportional. Inversely proportional. And so we're talking about, again, the weight of the entire object. We've got the density of the object and the volume of the object, both entirely. But for the buoyant force, it's the density of the fluid and just the volume that is submerged in this case. And so what if I told you for a second that 10% was submerged and 90% of the volume of this object was above the surface? So ultimately, this would be an indication that this thing's not just got a little bit lower density than water, but a lot lower. Because it turns out the closer it gets into density with water, by the time you equal the density of water, that's an object that's just going to hang suspended in water anywhere you put it. So, and ultimately, it's not going to have any of its surface above or any of the object above the surface of the fluid at that point. And by the time you make it a greater density, it's just going to sink to the bottom, right? So, well, it turns out that the lower you make that density, the more this object's going to have more and more of its volume above the surface, the lower its density becomes relative to that of the fluid. And so in this case, if we look here, volume of the object versus the volume submerged, we're saying that the volume that is submerged is just 10% of the entire volume of the object. The volume of the object is 10 times bigger than the volume that is submerged right here. So this is 10 times bigger. Well, but again, these are equal in magnitude, opposite in direction. If the volume of the object is 10 times bigger than the volume submerged, well, then the density of the object must be 1/10 of the density of the fluid. And we're going to derive something new now. So right off your handout here, we got another equation here that the percent that is submerged, make sure I write it exactly as I put it on your handout there, is equal to the density of the object relative to the density of the fluid times 100. If you only wanted the fraction that was submerged, well, then you just leave off the times 100, right? But it's just a ratio of the densities. And so again, in the example we've got here, so if only 10% is submerged, it's because the density of the object is only 1/10 the density of the fluid. Cool, so nice little principle to derive here. Cool, and again, the more you have above the surface, the less you have below the surface, the lower the density. The more you have below the surface and the less above the surface, the higher the density. But in both cases, as long as some is above the surface and it's floating, it's still gonna have a lower density than the fluid itself. Well, one other thing to note here, so this ratio of the density of a substance relative to the density of water, as long as we're talking about in water, we can write this a little bit different. And we can say that the percent that is submerged, and obviously water is what you're going to be dealing with more often than any other fluid. So that relative density to the density of water is the specific gravity. And so as long as we're talking about in water, so the percent that's submerged is just equal to the substance's specific gravity times 100, because the specific gravity is its own density relative to that of water as the fluid. All right, first question here says, a piece of styrofoam, density of styrofoam is given as 40.0 kilograms per meter cubed, with a volume of 0.010 meters cubed is held completely submerged underwater. What is the magnitude of the buoyant force acting upon it? So we just want to calculate that upward force known as the buoyant force. We've got a lovely formula for it. Keep in mind, again, it's equal to the weight of displaced fluid, which is going to equal the density of the fluid times the volume that is submerged, which is the entire object in this case, and then times gravity. And we know all these numbers. So density of water, you definitely want to know that one, is 1,000 kilograms per meter cubed. That's the one density you're on the hook for. So we're given that the volume of this piece of styrofoam is 0.010 meters cubed, and gravity 9.8 meters per second squared. So we could probably do the math in our heads here. So multiplying by 1,000 by 0.01 is just moving the decimal back 2 places to get 10, and 10 times 9.8, jumping straight to the answer. Here's 98. We want 2 sig figs based on the volume, so 98 newtons is our buoyant force. All right, second question here. So it's going to look really similar here, but a piece of iron, and the density of iron is given as 7,870 kilograms per meter cubed, with a volume of 0.010 meters cubed, is held completely submerged underwater. What is the magnitude of the buoyant force acting upon it? And here's the deal. It's still got the same volume as the styrofoam from the previous problem. Now again, iron's way more dense and its weight is way bigger than that of the styrofoam, but they both had the same volume that was completely submerged. The density of the fluid hasn't changed, even though the density of the objects has, and gravity hasn't changed, and it's the exact same calculation. Nothing has changed. 1,000 kilograms per meter cubed is density of water. Volume of the iron in this case is 0.010 meters cubed. Gravity is still 9.8 meters per second squared, and the buoyant force still comes out to 98 newtons. All right, next question here. A piece of balsa wood has a specific gravity of 0.13. What is its density? First question. Second question, what percent of its volume is submerged for a piece of balsa wood floating in water? All right, so we'll start with what is its density. And you got to remember that specific gravity is just an object's density relative to that of water. And since it's got a specific gravity of 0.13, that means its density is only 0.13 times that of water. Well, water is 1,000 kilograms per meter cubed, so 0.13 times 1,000 means the density of this balsa wood is going to equal 130 kilograms per meter cubed. And again, keep in mind that specific gravity is just equal to, let's write this better, specific gravity is just equal to an object's density, or density of a substance, relative to the density of water. So if you want the density of the substance, you just have to multiply the specific gravity times the density of water. And 0.13 times 1,000 is 130 kilograms per meter cubed. All right, second half of the question, what percent of its volume is submerged for a piece of balsa wood floating in water? Now, if you've just simply memorized the formula, and it's probably worth doing, truth be told, then in this case, you can just say the percent submerged is just the density of the object over the density of the fluid times 100. If the fluid happens to be water, then it's just the specific gravity times 100. And if you take the specific gravity of 0.13 times 100, you'll see that just 13% is going to be below the surface. So this piece of balsa wood is mostly above the surface. We got 13% below the surface, that's the percent that's submerged, and 87% above, just from our simple formula right here. And so again, the density of the object, 130 kilograms per meter cubed, relative to the density of the fluid, 1,000 kilograms per meter cubed, and then times 100. And again, 130 over 1,000 is the specific gravity when we're dealing with water, and that was again given as 0.13 times 100 is where that 13% comes from. Now be careful, this relative density times 100 gets you the percent that is submerged. But if the question actually asks you what percent is above the surface, well then you need to subtract from 100. And had that been the case, it would have been 87% instead. But that ratio of the densities, the object to the fluid, that's what gets you as the amount that's below the surface. One other thing to keep in mind, when we're dealing with water, water's density again is 1,000 kilograms per meter cubed. When you reach exactly half, your substance is exactly half that of water, 500 kilograms per meter cubed, well, that's when you'd have half of the above and half below the surface. It'd be equal. Anything lower than 500 kilograms per meter cubed means you're going to have way less below the surface and more above the surface. Anything between 500 kilograms per meter cubed and 1,000 kilograms per meter cubed means you're now going to have more below the surface submerged and less above the surface. So just kind of some benchmarks to keep in mind when dealing with the percentage that is submerged. All right, the next question is very similar. It says a piece of ice now has a specific gravity of 0.92. What is its density? And what percent of its volume is submerged for a piece of ice floating in water? And so now with the specific gravity being 0.92, we have to multiply the density of water by 0.92. And 0.92 times 1,000, so in this case for the ice, is 920 kilograms per meter cubed. So that's the density of the ice. So, and again, ice is water in general is one of those funky substances where the solid phase is actually less dense than the liquid. So I can think of one other substance for which this is true, and every other substance I know of, the solid's more dense than the liquid. So water is really unique in this case. Second half of the question again says, what percent of its volume is submerged for a piece of ice floating in water? And now, notice we're getting way close to 1,000 kilograms per meter cubed. We're definitely higher than 500 kilograms per meter cubed, where half of it would be submerged and half above the surface. So now we've got this piece of ice where most of it is actually going to be below the surface instead of above the surface. So, and in this case, again, with a specific gravity of 0.92, so it's 92%. So 920 out of 1,000 in this case instead is 92%. That is submerged only 18%, I'm sorry, 18, I can't add up to 100. How about just 8% above? Cool, so this is why, the old phrase, you can only see the tip of the iceberg. And that's true, the tip of the iceberg represents only 8% of the entire iceberg. More than 10 times of it, of what you see above the surface is below the surface. All right, next question. Says a metal alloy has a density of 4,000.0 kilograms per meter cubed. A block of this alloy with a mass of 100.0 kilograms sits completely submerged on the bottom of a freshwater lake. What is the normal force acting on this block? So we want to start with a free body diagram here. So this object still has a weight associated with it. It has a buoyant force, which is the new force in this chapter. But it's sitting on the bottom, so there's also going to be a contact force, that normal force, as well. And in this case, it's in equilibrium. It's just sitting there. It's not accelerating. There's no net force or acceleration in the y direction. So the sum of the forces in the y direction is going to add up to 0. And we can see that the normal force and the buoyant force point up, so we'll make those positive. So we got the normal force plus the buoyant force minus the object's weight, since it points down, all adds up to 0. And if you rearrange this, you can see that the normal force is going to equal the object's weight minus the buoyant force. And now we've got some plugging and chugging to do. So the object's weight, that's just going to equal mass times gravity, which in this case we're given, so 100 kilograms times 9.8 meters per second squared. So we can see that that's going to come out to 980 newtons. We'll substitute that in. So 980 newtons, and now we got to subtract off that buoyant force. And keep in mind that buoyant force, again, is equal to the density of the fluid times the volume of the object that is submerged times gravity. Well, the density of the fluid, this is water, so that's just 1,000 kilograms per meter cubed. But now we need the volume of the object, and that's not actually given in this problem. So, but keep in mind that density is equal to mass over volume. If you rearrange this, you can see that volume is equal to mass over density. So in this case, if I want the volume of the object, well, I know the mass of the object and I know the density of the object, and I can find its volume as a result. And so in this case, the mass of the object was given as 100 kilograms. The density was given as 4,000 kilograms per meter cubed. We can see that the kilograms are going to cancel, and this is going to come out in meters cubed. In this case, I'm just going to cross off a couple of zeros, and I'm going to leave this as a fraction for a second. So it's 1 over 40, which should be 1 over 4 is 0.25, so 1 over 40 should be 0.025. But I'm going to leave this 1 over 40 meters cubed, and we'll substitute that right back in here for our buoyant force. And then times gravity of 9.8 meters per second squared. I think we'll let our calculator do some of the work and the heavy lifting for us here. So 1,000 divided by 40 times 9.8. It's going to get us 245 newtons. And we'll substitute that right back in down here. And in this case, 980 minus 245 gets us 735 newtons. And how many sig figs did we want? Looks like we want 4 sig figs, so we'll tack on one more and just make it 735.0 newtons for that normal force. So the next question reads, a 100.0 kilogram block has a density of 2,000 kilograms per meter cubed. The block is completely submerged in a freshwater lake and lies on a scale on the bottom of the lake. What does the scale read? Now, this question sounds a little different than the last one, but we're looking for the reading on the scale if it's sitting on the bottom of the lake. Well, again, what a scale ultimately reads is normal force. So you're pushing down on the scale exactly what the scale is pushing back on you with. The scale reads normal force technically. Well, in this case, because you're underwater again, part of your weight is being balanced by the buoyant force. And so the scale doesn't actually, you're going to read your entire weight, only a portion of it. That's why you appear to be lighter underwater. Your weight's no different. It's just your buoyant force is counteracting part of that weight so that the normal force doesn't have to counteract all of it by itself. All right, so very similar question then. We're looking for the normal force. The only thing that's changed is that the density of this 100 kilogram block is no longer 4,000.0 kilograms per meter cubed, but 2,000.0 kilograms per meter cubed. So how's that going to change our calculation here? Well, one, it's definitely going to change the calculation of the buoyant force right here because the volume is going to be different. So its weight is no different. 100 kilograms, 9.8, 980 newtons for the weight. That's no different. What is different? So is going to be this calculation of the buoyant force and therefore the overall normal force in this case. So if we go back here, this volume is going to be different. So the density of the fluid, gravity hasn't changed, but the volume has changed because the density has changed. And so going back over here, so volume is equal to mass over density, still 100 kilograms, but the density, instead of being 4,000, is now 2,000 kilograms per meter cubed. And cross off a couple of zeros. We get 1 over 20 this time. Meters cubed. We'll substitute that back in right here for the volume of the object, because that is the volume that is submerged. We'll put our calculator back to work here. So 1,000 divided by 20 this time, times 9.8. And it should be, yeah, exactly double what the last one was, since we're dividing by 20 instead of dividing by 40. And we get 490 newtons for that buoyant force. All right, so coming back here, 980 minus 490. And we see now that the normal force is lower than in the last problem. And we should see that this is probably exactly half, right? So 980 minus 490 should give us 490, and indeed it does. And so the normal force is also 490 newtons. All right, so a couple things we got to factor in here. So I never redrew the diagram here, but we had 100 kilogram mass in either way. So I felt like, well, we don't really need to redraw it. However, if we're trying to compare the drawing from this one to the previous problem, with the only difference being that the density was now half as much. Instead of 4,000 kilograms per meter cubed, it's now 2,000 kilograms per meter cubed. Well, with a lower density, what that really means, with half the density, that would mean that this object had to be twice as big. It had twice the volume this time. Instead of 1 over 40 meters cubed, it's now 1 over 20 meters cubed. So as a result, because it has twice the volume, that's why it has twice the weight of displaced fluid, twice the buoyant force as the previous example. So the last question here says, if an object normally weighs 600.0 newtons and while submerged in water, it has an apparent weight of 400.0 newtons, what is the density of the object? Okay, to solve for the density here, we'll set up a free body diagram. And in this case, the weight still points down. So, and that weight, whether you're in the water or out of the water, if you're normally 600 newtons, it's still 600 newtons. It just feels less, right? Because part of that weight is being countered by that buoyant force, so that the normal force doesn't have to counter all of the weight. And that's ultimately what a scale reads as normal force, recall. And so in this case, that normal force is the 400.0 newtons. Not too bad from here just to see and be like, oh, well, some of the force in the y direction is equal 0. There's no net force or acceleration in that y direction. So if there's a total force of 600 newtons down, there must be a total force of 600 newtons up. Well, there's 400 of it. The buoyant force has to account for the rest, and therefore be 200 newtons of it as well. Okay, now from here, we could kind of take a formal approach to this, but we're not going to. We're going to take a little bit different look at this and get to the solution a little bit faster here. So if you recall that weight is equal to mass times gravity, and keep in mind that density equals mass over volume. So mass is therefore equal to density times volume. We'll substitute that in, and we see here we're going to have density times volume times gravity, where this is the density of the object, the volume of the object times gravity. And then buoyant force. We've got a formula for the buoyant force here, which is the density of the fluid. So again, this is the weight of displaced fluid. So it's the density of the fluid times the volume that is submerged. Well, in this case, it's completely submerged. So the volume that is submerged is the same as the volume of the entire object. So I'm going to write that in as well, and then times gravity. All right, so here, notice the similarity in these two parts of the calculation. The only part that's different is whose density are you using here. So gravity is the same, the volume is the object completely submerged, so the volume submerged and the volume of the object is the same. And so the density of the object versus the density of the fluid, that is your big difference. And so the thing I want you to see here is that if you take the weight of the object relative to the buoyant force, in this case, so ultimately you're just going to get the density of the object relative to the density of the fluid. It's just this one over this one. So, and the numbers often are given to you nice so that you can reason it out in such fashion. And so in this case, this comes out to 600 newtons over 200 newtons. And so ultimately, if the weight of the object is 3 times bigger than the buoyant force, it's because the density of the object is 3 times bigger than the density of the fluid. Well, water's the fluid. We know the density. It's 1,000 kilograms per meter cubed. What's 3 times bigger than that? 3,000 kilograms per meter cubed. Or in this case, looks like I've got to get 4 sig figs out of that, so 3.000 times 10 to the third kilograms per meter cubed is the density of the object. And so you can get that simple ratio. As long as you know the weight of the object and the buoyant force, that's just equal to the ratio of the corresponding densities as well, and you can solve for the one you want. If you found this lesson helpful, consider giving me a like. Happy studying.